Good morning, my fellow scientists. It is Thursday, July 13th, 2017, and I want to talk to you about battery separators. If you're not familiar with the idea of a battery separator, we need only look toward the original galvanic cell to understand why and how a battery separator works. That salt bridge is the separator. It serves two functions. You need to insulate the two chemical reactions that are happening in any battery. You don't want the two reactions to just happen spontaneously reacting with one another. You need them to happen in isolation so that they can provide an electric current. And the second function of the separator is to allow for charge transfer between the two cells. If you have an electric current, you're moving electric charge from one side of the battery to the other. And if you're moving an electric charge, one side is going to become negative and the other side is going to become positive. And for a battery, that's a bad thing. Now, capacitors work that way. Capacitors, you accumulate a charge. But in a battery, that just very quickly adds up to not moving charge anymore. The more charge you add to one side, the more it resists additional electrons moving through. So you have to have something to balance your electrons. So for most batteries, that means that negative charges move across the wire and positive charges move across the salt bridge. So salt bridges need to be electrically insulating and ionically conductive. The old salt bridges were made of some sort of gel and a salt. That salt has enough positive charge in it such that ions can move into the salt bridge on one side and out on the other. Net result, the whole thing stays electrically neutral. So that's the point of a salt bridge, that's the point of a separator. But modern batteries don't use this design. Modern batteries have some sort of membrane separator. And that's because of the high-performance materials that chemists and chemical engineers know how to make. So you can have a polymer membrane that is so electrically insulating and so ionically conductive that even a very thin membrane of that material can do all of the chemistry necessary for the battery. So instead of needing this long, thick salt bridge, you can have a very thin layer. I tried to build such a layer day before yesterday, and it did not go well. The net result was that my very thin layer was simply too electrically conductive, and the fact that the layer wasn't sealed at the edges didn't help either. So a thicker layer could help overcome that, but that adds to the resistance of the battery and you get less energy per unit area. And of course, it also adds mass to the battery without contributing any energy storage capacity, which means your battery is heavier and not more energetic. So that's not a great thing either. So I see two options. One, use a commercial membrane, which are expensive and not something you can fabricate yourself. Or two, admit that I need a thicker membrane and deal with the consequences. So for now, let's explore that option. So how's that going to work? Previously I had a really thin membrane separating my anode chemistry, which is basically iron wire, right up against that membrane, from my cathode chemistry, which was a aluminum backing plate with iron EDTA in front of it. And the gist of it was that that iron could exchange enough material with the iron EDTA to discharge the battery without providing any electrode current. So the easiest way to avoid all that is to add more space between the two. So it doesn't have to be fancy membrane chemistry like I had earlier this week. Instead, I can just add an agarose pad to space everything out, add a little more electrical insulation. So tune in tomorrow. We'll talk about how that thicker separator worked out. We'll talk about more information on battery separators. We'll talk about chemistry and science and progress in technology. We update Monday through Friday, and we talk about all that and more here in the Island Lab.